last time what we were looking at was the ring of polynomials, right? So we had this set R bracket X, and we showed that R bracket X, the set of polynomials where the coefficients come from R, actually is a ring under the operations of addition and polynomial multiplication. All right, so we've got a ring. Now, in most cases, right, so in most cases, we will be considering F bracket X, where F is a field, right? So our main study, our main, what am I trying to say? Our main object of interest is going to be F bracket X, where instead of just having an arbitrary ring, we actually require our coefficients to come from a field. Right? So that will be the main thing that we study. Now, even with F being a field, there is absolutely no hope, right, that F bracket X is going to be a field, right? So there is no hope that F bracket X is a field. No chance. In fact, maybe I should say no hope, right? There's no chance. Or no way. Right, so I want you to just think about that for a second. What would it mean for F bracket X to be a field? Well, it would mean that every non-zero element has to have an inverse with respect to multiplication, right? Or another way to say this, every non-zero element is going to be unit. Well, think about non-zero degree polynomials. Anything with degree greater than or equal to 1 is not going to have an inverse living inside F bracket X. Right, so there's no chance that F bracket X is going to be a field, but here's what we are going to see. So this is going to be the next thing we prove, actually. So we will see that if, let's say, capital D is an integral domain, then D bracket X is an integral domain also. Okay, so that's good, right? These are not going to be fields, right? The ring of polynomials is not going to be a field, but as long as the coefficient ring is an integral domain, then the ring of polynomials will be an integral domain. In particular, right, F being a field is an integral domain, so F bracket X, it's not going to be a field, but it will be an integral domain. All right, so the field of quotients of F bracket X is denoted F parentheses X, right? So there will be times when we want to study this ring right here. So remember, anytime if you have an integral domain, in particular F bracket X, there's a corresponding field of quotients. This will be the notation for the field of quotients of F bracket X. And you might want to think about what the elements of F bracket X look like, right? In fact, maybe I should just say in parentheses, right? Who is F bracket X? Well, they will be equivalence classes. And if you write them as fractions, the way you can think of them is polynomial over polynomial. That's the set of rational functions. So this is the ring or the field of rational functions. Over here we said there's no way that F bracket X is a field, right? There's not going to be inverses. So what does the field of quotients do? It gives us inverses, right? It gives us, it turns everything into a unit, and the inverse is going to be the obvious thing. It'll be the reciprocal 1 over the polynomial P of X. So we'll come back and study all of this in more depth, but let's get to what we want to prove here. So this is going to be theorem 22.2. If capital D is an integral domain, then d bracket x is an integral domain. Okay, so what do we need to do? We need to show that there's no zero divisors inside d bracket x. And so let's choose a couple of polynomials. So let's let, or for our proof, let's let, say, p of x and q of x in d bracket x be non-zero. All right, so what does that mean? Well, both p of x and q of x, those are polynomials, and so what this means is that there's at least one non-zero coefficient corresponding to each of p and q. Right, so we can write them both out. So let's write p of x equal to, say, a0 plus a1x plus dot 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 plus a sub m x to the m. And we got to write q of x also out. So q of x equals b0 plus b1x plus dot 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 plus b sub n x to the n. Where here I'm thinking of the degree of p of x is equal to m and the degree of q of x is equal to n, which means that a sub m is non-zero and b sub n is non-zero. So to finish this off, where a sub m and b sub n are not equal to 0. And also, so remember when we first wrote out the notation for a polynomial, I used this sort of infinite series looking notation, sum n equals 0 to, or let me use an I equals 0 to infinity, a sub I, x sub I, where I then assumed that there's only finitely many non-zero a sub i's. Okay? So I could use, it gets a little clunky using the infinite series notation. I'll use it when I need it, but most of the time we're going to write out polynomials the way we know they look. And so what we're doing, when I write this out and I stop here at a sub m, what I'm saying then is that a sub n plus 1, a sub n plus 2, and so on, going on forever, all of those are 0 coefficients, right? Same thing here. Every coefficient greater than, or with subscript greater than n in the polynomial q of x is equal to 0. So here, so in fact, I could say this, and I'll just say this in parentheses, and a sub k equals 0 when k greater than m, and b sub k equals 0 when k greater than n. In other words, then, this right here, a sub m, is the last of the non-zero coefficients. If we start from 0, a1, a2, a3, some of these might be 0. A sub m is non-zero, and there are no more 0 coefficients. Same thing with q. I'm probably saying this a bit too much, but I just want to get the notation down. This is typically how we're going to write polynomials. We're not going to use this infinite series notation unless we absolutely have to. Okay, so now when you multiply p of x times q of x, what's going to happen? Well, you're going to get a bunch of mixed match coefficients right here, a0 times b1 and b2 and b0, blah, blah, blah. All of these are going to be multiplied, but, and I don't know exactly what they are because some of these coefficients could be 0 throughout here, but one non-zero coefficient that I'm guaranteed the polynomial p of x times q of x has is am times bn. So then p of x times q of x has the term, it will be a sub m bn x raised to the m plus n. And, well, we know that a sub m is non-zero. We know that b sub n is non-zero. And since D, we're working in D, which is an integral domain, and since D is an integral domain, we have that AM times BN is not equal to 0, right? That tells us then that P of x times Q of x is not the 0 polynomial. So it follows that P of x times Q of x is non-zero. And so, let's write a final sentence. Therefore, D bracket x is an integral domain. Right, and that completes the proof. We showed that anytime you take two non-zero polynomials, you get a non-zero polynomial, which means that D bracket x has no zero divisors. Oh, I guess I should point out, remember, what is an integral domain? An integral domain is a I really should not conclude. Let me just back up here for 1 second. Sorry, I'm gonna erase that right there. So what I've shown is that there's no zero divisors, but I need to remind everyone, right? So let me just write one more concluding sentence here. From theorem 22.1, we have that D bracket x is a commutative ring with 1. Now I can say the final sentence, therefore we have an integral domain. So remember, an integral domain is a commutative ring with unity and no zero divisors, right? So therefore, D bracket x is an integral domain. Sorry, I just wanted to insert that last sentence right there just to be complete. Remember, we showed that there's no zero divisors. We needed to also just point out we've got a commutative ring with unity also. One thing to notice from this proof, I'm not going to write this as a corollary or anything, but we'll just say it's sort of an observation or a note. So note, from the proof, we have the following. If we're taking polynomials from an integral domain, so we have that when we do degree, so the degree of P of x times Q of x, how does that work? Well, notice we had degree of P was equal to M, degree of Q was equal to N, and when you multiply this out, this would be the term of highest power right there. So the degree is M plus N, right? Which means that it's additive in this sense. So degree of P of x plus degree of Q of x. And notice, and this is in part why we choose the degree of the zero polynomial to be negative infinity. So notice here, if I do constant polynomial times some other polynomial, constant polynomial is 0 as long as it's not the zero polynomial. When I put the zero polynomial, we multiply, we'll get the zero polynomial. And so what we'll get is negative infinity plus some finite number, and so it actually works out to be minus infinity over here also. So the reason, in part, that we choose the degree of the zero polynomial to be negative infinity is that this forces or allows this formula to be true for all possible polynomials, including when one of these is the zero polynomial. Couple examples here. So since Z is an integral domain, so is Z bracket X. Same example, or in the setting here, since Z2 is a field, Z2 bracket x, it's not a field, but it is an integral domain. Okay, so as we continue our discussion, I want to describe, so we need to create a little bit of machinery that's going to allow us to work with polynomials. So let's let F be a subfield of the field capital E. Now, you might say, hey, whoa, you haven't even defined that term subfield. Well, okay, what do you think it means? It means exactly what it should mean. It means that F is a subring of E, and F happens to be a field as well. So I'll just say, what does that mean? It means that F is a subring of E, and F is a field. Now, given some element, let's call it alpha, in capital E, define, what I want to do is set up a function, or I want to define a function here. So this function phi sub alpha is going to go from f bracket x to E, and the way we define it is going to be by, so let's see, it's going to be phi sub alpha of the polynomial a0 plus a1x plus dot 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 plus a sub n x to the n. Right, so I'm going to plug in a polynomial from f bracket x. And we're going to do the obvious thing. What I want to do is I want to plug alpha in for x. So this is going to be a0 plus a1 alpha plus a2 alpha squared plus dot 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 plus a sub n alpha raised to the nth power. So notice, because alpha lives in E and so do all the AIs, right? The AIs come from F, and F sits inside E, which means that each of those AIs lives inside E. So this expression right here gives us an element of capital E. So, right? So this makes sense as a function. And this is one of the key tools. This is important. This is crucial in studying polynomials. Sorry, I spaced out for a second. I should point out what I mean here. Right? So notice over here, this we call a formal sum, right? We don't really assign any meaning to this symbol plus right here. Nor do we assign any meaning to a1 times x. It's just an object, right? A bunch of symbols written down with pluses in between them, right? We don't think of this as a function per se. But over here then, what do we mean? That plus right there, that's the plus in E. a1 times alpha. That is multiplication in E. A2 times alpha squared, that's multiplication in E also. So let me write down what I want to say about this thing now. So this function is one of the key tools used in the study of polynomial rings. Let's just say in the study of, let's say polynomial rings. It has a special name, so it's called evaluation at alpha. I think I mentioned earlier on that these evaluation maps are important, and here is a very important evaluation map, right? Anytime we have this setup, right, we can create this evaluation map right here, and we'll definitely make use of this. And this next theorem, let's see how much time we've got here. Oh yeah. So this next theorem is going to tell us why this mapping is useful. So this will be theorem 22.3. So if, I'll say it like this, if F, I want to say if F is a subfield of E, if F is a subfield of E and alpha is an element of E, then the evaluation mapping phi sub alpha from F bracket X into E is a homomorphism. And in this setting, and now we've got group homomorphisms, we've got ring homomorphisms. You need to understand when we say the word homomorphism, what it means from the context. In this case, we are talking about a ring isomorphism, right? F bracket X is a ring. E, yes, it's a field, which means it's a ring, and so this is a ring homomorphism. And at key points in this class, we're going to use this theorem. Okay, so the proof is pretty straightforward. We really just crank it out. And this is one case where it's more convenient just to use the sigma notation when we're talking about the polynomials. So the proof goes like this. So let's let p of x, let's write that out. It's going to be the polynomial with alpha for the coefficients. So ai, I just said alpha, sorry, ai x to the I, and q of x equal to some bi x to the I, b polynomials in f bracket x. There are stopping points. If you want, this could be a degree m polynomial, so you can say I equals 1 to m here. You can say I equals 1 to n here if you like. So then, and remember when we write this out, right, so this what this is saying is that the degree of the polynomial p of x is equal to m, the degree of q of x is equal to n. I really don't want to worry about these. I'm in fact, in the rest of the proof, I'm not even going to write the stopping points here. Just know that we're running as I goes from 1 to some number, right, m, some number n. So then when we look at p of x, homomorphism, so then phi sub alpha of p of x plus q of x is equal to phi sub alpha sigma ai plus bi times x to the I. This is what you get when you add p of x and q of x. Now when we plug alpha in, right, doing our evaluation, we get sigma alpha I plus, or sorry, I said alpha I, ai plus bi times alpha raised to the I. And now this is happening inside E. The distributive property holds, and so this is equal to sum ai alpha I plus sum bi alpha I. And that's exactly evaluation of p of x plus evaluation of q of x. Now we need to show that the multiplicative property holds. So we can say also, if we do phi sub alpha of p of x times q of x, that is going to be phi sub alpha of the polynomial. So let's call the coefficients, right? When you multiply these coefficients, let's call the coefficient d sub I. So it'll be d sub I x sub I. And I'll remind you who this d sub I is in a second, but let me plug in alpha here. So this will give me sigma d sub I alpha raised to the I, where d sub I, that's going to be sum n equals 0 to I, and it will be a sub n b sub I minus n. Just the usual coefficient formula for multiplication. Now what I want to do, I need to compare this to phi sub alpha of p of x times phi sub alpha of q of x. So let's just write that out. Phi sub alpha, so we'll say and, phi sub alpha of p of x times phi sub alpha of q of x is equal to, so let's see what we're going to get. Phi sub alpha of p of x is going to be sum ai alpha I. And then for phi sub alpha of q of x, that's going to be sum bi alpha I. And now I'm supposed to multiply these two expressions together. These two expressions are living inside inside E. And so just apply the distributive property. And what do you think you're going to get? Well, it's going to have us multiply the coefficients in exactly the same way that we would multiply coefficients of polynomials. In fact, I mean, let me write this out now. This is exactly sum di alpha I. So what is this theorem telling us? It's telling us that if you want, you can multiply and plug in alpha. Or if you prefer, plug in alpha and multiply. All that's going on, I mean, what's the difference between p of x and the evaluated version? You replace x with alpha. That's all that's happening. And so, if you want to multiply and then plug in alpha, or plug in alpha to both and then multiply, you're going to get the same thing, right? So that's the end of the proof. And one thing that I want you to observe, let's say note, if it restricts, or restricting, so if I just take the function phi sub alpha and restrict it to the constant polynomials, right? This gives an isomorphic embedding of f into E, right? So this evaluation mapping allows us to sort of take f and put it into E as it's already sitting. Okay, so that's a good place to stop. We will see you next time, and we'll see how to make use of this theorem in the next time.